So we are to study how to solve the initial value problem y prime equals to f of xy with the initial condition. Okay, I need to give you some introduction. Okay, about solving differential equations. Okay, so and most of you must have taken differential equations class like Math 334. Okay. So many times we may have no idea how to solve this equation analytically. But we still can say something. Why? Because you know the meaning of y prime dy dx. Okay, it's the slope of some curve at a point, right? Okay, so in that case, given that we even have no idea how to solve it by hand, now you just based on the given function like this here, y prime equals to x squared minus x. You choose many points. You calculate. You find here, given that it's this point, you figure out it's a slope. You draw its slope, and then at the origin that's 0. Okay, it's a line segment with that slope. Okay, this is a point, and you calculate its slope. And you draw so many dashed lines, and the more the better. And so such a graph is called the slope field, and it helps. And why? Because there is such a theorem. There is a theorem of existence and the uniqueness of the solution to such an initial value problem. It says, yes, if f and df dy are continuous in the neighborhood of the initial point, okay, and then in that neighborhood there is a solution, and the solution is unique. Okay, we go to this very slope field. You say, how about if initial point is this point? Here you have such a point, therefore there is a curve, right? It's a unique curve. If it passes through that point, and you can figure out there is a curve. Okay, that's this. Okay, and when we solve differential equations, if we can find analytic solutions, that would be nice. An analytic solution is a solution. Say, if you given this initial value problem, if you can express y as a function of x, eventually, that's called an analytical solution. Or if you can express, you can set up the solution like a relation like x squared, say, plus y squared is 2. If you say, hey, this is a solution to this, if it is satisfied that equation and that initial condition, yes, it's also an analytical solution. That you may call it an implicit solution. Okay, how about a numerical solution? Numerical solution, that means, okay, we divided this interval into many subintervals evenly, or from on this interval we will have x1, x2. We have many points or nodes. They are equally spaced. Okay, and now that's initial point. We always start from the initial point. Okay, and then we move on to the next point. Say from x1, the initial point, we move on to x2. After now this you have x1, y1. That y1 in this very initial value problem is y0. Okay, and now we try to figure out how about when x is x2, how about y2? If we that's our purpose. We need to figure out y2, x2, x3. They are never a problem. It's how to find y, the corresponding y value. x3, how about it's y3? We need to figure out that y3 and so on. And that's numerical solution. And you have x, you have y, all those x values, y values. Okay, at those points, nodes. And with MATLAB, LUO plus Mathly or Julia, you can simply, normally it's, MATLAB, LUO plus Mathly, you can simply use plot. It's hey, x, y are vectors or arrays of values. It's that simple. You can plot your solution. Okay. And when we find a numerical solution, the domain must always be given. Without this, what can we? Yes, at least the initial point is given. Now you should stop. Where to stop? We need to have the right end point. Okay, so a domain must be given. That's one case. The second case, as you already know, the whole process, the solution is incremental. We start from initial point and move on to next point to find all the corresponding y values. And there are two approaches. Okay, one approach is called a single step approach. When we move on from xi, yi, from xi, yi, such a point, we want to move on to next point, x plus 1, so I plus 1. Okay, to calculate this y plus 1, we only use xi, yi, at most xi plus 1. Okay, we will not use xi minus 1, xi minus 2. Okay, we'll not use this. Okay, so that's a single step approach. Multi-step approach we'll use, as you can see, to determine this y plus 1. We could use xi minus 1, xi minus 2, and their corresponding y value. Okay. And we have explicit method, we have implicit method. Okay, explicit method is a method when we calculate y plus 1, y sub I plus 1, we only use for, today we just focus on this topic. Please be advised that this topic of solving initial value problems is a huge topic. Okay. It needs multiple lectures or even a whole class to address it. Okay, so explicit method is this. When we calculate y plus 1, we only use xi plus 1 yi to calculate it. In other words, and you can say y plus 1 depends on xi plus 1 yi only, and all y plus 1 is a function of those xi plus 1 and yi. Okay, so that's explicit method. Implicit method is when we calculate y plus 1, we will use information like xi plus 1, yi plus 1. Hey, wait, y plus 1, I don't know. How could you use it? That's a problem. And but if you have such a relation, and xi plus 1, yi, they are known. Therefore, such a relation in this equation, yi plus 1 is the only unknown. Therefore, you solve it. We will have a step, solve it for y sub I plus 1. Yes. You may say, oh, that's easy. No, it depends. And it depends on the equation. Some it will be quite tough to solve. Okay, that's why we have one chapter about which one solving nonlinear equations, right? If it's a nonlinear equation, it could be tough to solve. It takes time. Okay. And the explicit method is also called, the explicit method could be called a predictor, implicit method could be called a corrector. And finally, in today's talk, we will combine the two. Yes, it will be a great new algorithm. Okay. Okay, we also need to pay attention to errors in numerical solutions while we solving differential equations. Okay, runoff errors, yes. Normally we don't have much control on it, and we normally focus on the analysis or the control of truncation errors. And here is different. Okay, we will have a local truncation error. At each step, you could have its own truncation error, right? And if from the first step, that's exact solution. It's the initial condition. It's exact. We move on to the next point, x2, and yes, because x1 at x1, when we do calculation, x1, that very point x1, y1 is exact, no problem. When you do calculation, you calculate x2, you could have a truncation error, right? And at this fourth step. Now, when we move on to finding y sub 3, and itself has its truncation error. It's a log truncation error. And now the truncation error, yes, when we calculate x2, yes, it will be passed to that step 3 for y3. Okay, y sub 3. And it could be magnified. Okay, so we say we have the other type of truncation error. It's propagated or accumulated truncation error, and you can find the sample code. Okay, MATLAB or Julia or LUO plus Mathly, you run it. Especially you have yes some sample examples there. You use a little larger step size h, you will see, obviously, yes, in many cases. At the beginning, no error. The error, it's not no error, the error is 0, okay. And now you have some at the first step. Second step is getting larger, and third step larger. The error is larger and larger. Oh, yes. That's the contribution of this part, propagated truncation error. Okay, if we combine both the local truncation error and the propagated truncation error, yes, that's so-called the global or total truncation error. Okay, now remember we focus on this initial value problem. It's the first order initial value problem. Okay, and so for all simple step method, the solution look like this. Okay, xi no problem. From xi move on to xi plus 1, just add h, no problem. And the problem is how to find yi plus 1, right? Okay, how to find it? And as you can see, the idea is like this. As in Cal 1, you have a function y is f of x at a point. Now it's just a single variable function. This is a two variable function. Okay. a single variable function. We use which one? You have a curve at a point. We try to use its tangent line to approximate the curve locally. And this point is, say, hey, x0, y0. Therefore, the tangent line, how about the tangent line? The equation of the tangent line is y is y0, or f of x0 is y0 plus f prime at x0. X minus x0, right? Yes, is this. Okay. So, and now we find the tangent line at xi, xi. Okay, so, and now we want to find yi plus 1. yi plus 1. That's I plus 1x. So that's just h. So yi plus 1 is yi plus f prime of xi h. Yes, we have such a formula, and ignore this formula, that f prime. We just know this f prime of xi is a slope, right? Yes, that's it. So we have this. That's the way we find, okay, the general idea how to find y plus 1. And so, and how about this k? So there are different algorithms, methods. Okay, there are differences. Yes, can be seen through the choice of such a k, such a slope. The slope, yes, there are so many ways to choose. Okay. Euler's method. When we say Euler's method, normally we mean Euler's explicit method. Is this. Because xi, yi is given, therefore from this we calculate y prime, it's just f of xi, yi, right? We just use that very point. The value of f of x, y at that point. So we can use that as the slope. That's Euler's explicit method. Is that simple. Okay. So, and Euler's implicit method. Okay. It says, why should I use this? How about I use that point? Xi plus 1, yi plus 1. We say k, you choose k be f of xi plus 1, y plus 1. But the problem is you want to find y plus 1. Y plus 1 is unknown. That's a problem. So as I said, you already know, if for Euler's implicit method, yi plus 1 will be yi plus, you use that as the slope, f of xi plus 1, yi plus 1, that kh. Okay, so you just solve this for y plus 1. Okay, that's Euler's implicit method. And you can have other way to do it. Say like modified Euler's method. How about that? Hey, I use this. I find which one, the slope here. Through this, we use implicit method, explicit method to find yi plus 1 temporarily, TMP. You use this. You use which one? Euler's implicit method. You find this h. You find this temporary value at this point. You assume that's the very value. Therefore, next you find the very y plus 1. You use, hey, it's yi plus k. How about k? Hey, k, I use the average value of which one? F of xi, yi. That's the slope at this point. M plus f of x I plus 1, y I plus 1 is temporary value. Okay, you figure out such a one. That's modified Euler's method. Midpoint method is another way. He said, hey, you can figure out if you're, yes, we all are smart enough. We try to be creative, right? Okay, you can figure out your way. And another way is, hey, I just move to the midpoint here and just have a step. And I find, therefore, I use Euler's explicit method. I find that point, the midpoint value is which one? Xm, as you can tell, it's xi plus the midpoint x is given by half h, right? The slip says it's half h. And now use yi plus slope f x I yi, that's k, Euler's explicit method. Step size that h is half h. Yes, you figure out that point. You say, hey, this is xm, ym. Now you know its coordinates. Now you put it into this function, and now you keep yi plus 1. How about that? Will be yi plus k. What's k? K is the slope. We use the slope at the midpoint. That's f of x m, y m. M stands for midpoint. Okay, h. That's k. That one is kf's value, the function's value at the midpoint. Yes, that's midpoint method. And we have the Runge-Kutta method. The Runge-Kutta method, that's not a method, that's a family of methods. They're amazing. Okay. So, should we have one example? I just show how to do it. Okay, by hand. Okay, that's explicit method. Use this formula. Okay, that's initial point. Okay, initial point. It's given. Now we find we calculate y2. How about y2? How to find y2? You say use that formula. Y2 is y1 plus f of x1 y1 h. And we know y1 is 1. F in this case is x plus y. That's x1 plus y1. x1 is 0. y1 is 1. H is 0.5. Therefore, that's 1.5. So we just put here 1.5. And now we can move on to the next step of finding y3. Y sub 3 will be y2 plus f of x2 y2 h. y2 is 1.5. F of x2 y2, that's x2 plus y2 times h. That's 2, that's 1, that's 2.5. 2.5, and so on. We don't need to finish all. Okay. And implicit method, the same. Just do it. Okay. Again, we'll see. How about y2? y2 by this formula is y1 plus f of x2 y2h. y1 is 1. Again, f of xy is x plus y. Okay, it's x2 plus y2. y2 we don't know. H is 0.5. Okay, we have 1 plus 1.25 plus 0.5 y2. and you have y2 equals this, solve it. That would be nice. 0.5, y2 is 125, so y2 is what? It's 2.5. Okay, and you can find y3, y4. Okay, that's the summary of the methods we just mentioned. Okay, let's say explicit method, implicit method, and 3 modified method, midpoint method, except the second one, which is implicit method. All others are explicit method. Explicit method, you can just simply say we don't need to solve for y plus 1. Okay, just evaluate, get it. Okay, so now Runge-Kutta method. Okay, the family of Runge-Kutta methods itself is a big topic. Okay, I just show you the idea. If you read your textbook, possibly you feel it's just horrible. Okay, actually it's quite easy. Okay, of course it's not as easy as the methods that we just studied. Okay, it's this. We do calculation. We move on from xi to xi plus 1, right? Okay, now it's still one single step approach because xi plus 1 depends on xi. Sounds like this. Okay, actually it's way more complicated. It's this. On this interval x, on this xi plus 1, we will choose more points, representatives. Okay. xi itself will be selected, and they choose another point. It's a little way, yes, from xi, and we choose another point a little way from that point we just chose, and choose some other points. The points here you chose, you don't know their distribution. Okay, it depends on the order of the method. The order is this: how many points you choose. Simply speaking, you use 2 points, the order is 2. Use r points, the order is r. You choose r points here, choose r points here, and okay. With this initial one, you can figure out its slope because xi, yi are now unknown. When we move on to xi plus 1, xi, yi are unknown. Now, you choose this point. Through some way, you can figure out this point. You choose, say, like xi is plus some, say, a sub 2h. That a2, if h, given that h is positive, okay, a2 is some value like it's a positive number less than 1. Okay, so, and you can figure out this by the way, all the methods you studied, you can figure out at this point how about its y value. Okay, and at that point, therefore, at this point has its slope, or this point contributes its slope because you know its xy coordinates, and you calculate more points, and given that you can find the y value, and you can find its slope. So for those r points you chose, each point has its slope. Now, with this general approach, we should make a k. We choose a k through all those slopes, okay, slopes, and we find their what? Weighted mean. The weighted mean. Okay, so okay, now that's the essence. That's the very idea. If you know this, the algorithms are not so difficult to understand. Okay, now is this. Okay, we choose, given that the order is R, we will weighted mean is this. You have a K1, K2, Kr, right? Their slopes, and their weighted mean. So each one has its weight, each term. And for weighted mean, if you studied in statistics, you know is this. The sum of the weights is 1. Okay, so the weights here, in this case, in statistics, normally the weights should not be negative here. It could be negative, okay. Some positive, some negative. Okay. Now, K1, the fourth point, as I just said, is xi. Therefore, its slope is f of x1 yi. Yes, you figure out this. And K2, how about this? Given that this point is A2H, it's xi plus this. Okay. Therefore, you construct K2 this way. K2 is the value. Its x is this. How about its y? Y, you imagine you use K1 to calculate. Use yi. Itself is it follows this formula. So the idea of Runge-Kutta methods is which one recursive. The idea itself is recursive. All the development analysis of the steps, yes, it's so then themselves are recursive. Interesting. Okay. So you follow this, you calculate. Oh, it's this. That's why you use the num K1. You only have a K1. One slope is num. You find it. This is actually what method? That's what method? Euler's explicit method. Okay. And now you calculate K3. And K3, that's another point. It's this point. It's xi plus A3h. That A2, A3 are positive number. Both are less than 1, and A2 is less than A3. Okay, you see, you calculate K3 is the slope at this point. You should know x value, that's this. Y value, okay, how about y value? Y value, no, it's this. Y value, you already know the slope at this point, K1, K2. Now, through K1, K2, you calculate this point. Okay, and that K1, K2, that K itself is what? It's like this, weighted mean. Okay, so and now as a KR, you calculate KR is this point. KR is here. You go. If this KR, that's XI plus ARH. Okay. So at that point, the slope is given by f of that x value. How about y value? You follow this formula. It's yi plus kh. And h is this value. Yes, you have this ARH. Okay. And how about its slope? You already have those points, their slopes. Find their, which one? Find their weighted mean. Find the weighted mean of K1, K2 up to KR. Yes, you can do this. Okay, so I love this method. Okay, this approach. But really, if you want to understand it, it takes time. Okay, and this method itself, you can use Taylor series expansion to analyze its local truncation error. Is this for which one? For the Runge-Kutta method of order R, the local truncation error is this. Wow, that's good. The larger R is, yes, the better approximation we will have. Oh, that's theoretically. Okay. and the global truncation error is that. Okay. So, okay, say for example, for the second order, we use 2 points from xi, x plus 1. We choose xi is 1 point, another point, that's a2h. Okay, so you can figure out this point, k1 is given by this, k2, yes, it's this. And we'll use Cal 3, he has knowledge started in Cal 3 and even in advanced calculus. Especially here, we'll use the Taylor series expansions of multiple. Here, it's 2 variable functions, f of x, y, 2 variable functions, Taylor series expansions. Anyway, and the chain rule, and then you figure out the relation. Here you have a2, right? b21 and c1, c2. Anyways, can set up such a relation through those knowledge just covered by calculus 3 and advanced calculus. And it turns out such a system that's not easy to solve. Okay, it's because it's not linear. Okay, so it may have many solutions. Okay, so actually the modified Euler's method and the midpoint method are 2 specific what second order Runge-Kutta method. Therefore, their global truncation error is each one is big O of h squared. Okay, and okay, say you can verify it. That's midpoint method. That's that's a modified method, Euler's method, midpoint method. They each satisfy the relation. Okay. Third order, the same. You choose 3 points. Xi is a point. You choose 2 more points. Okay. You set up a relations, and then you set, and it turns out that you set up a system of nonlinear equations. The solutions are not unique. You have many solutions. So here are typically the commonly used solutions or methods eventually. Okay. The classical third order Runge-Kutta methods use this. Okay. This group of coefficients. Okay. And even fourth order, fifth order, oh my. In 1964, in those days, many people don't have access to computers. Wow. If you do it by hand fully, wow, that's a lot of work. You need to have great patience. That's why I tell students, my classes, yes, math. I try to love math. Math is a subject which helps us develop our patience. It can train our patience very well. Okay. So I cannot imagine how much work there will be. Okay. Seems simple. Okay. But it's not. Okay, we have finished that part. And finally, for single step approach, we have one more choice. One more one. That's combination of something. This method is called predictor corrector methods. The very algorithm is that you choose, you say our approach is always which one, yi plus 1 is yi plus kh, right? Okay, you choose one explicit method. You calculate y plus 1, or in some sense, something like to initialize it. Okay, and it only depends, that k only depends on which one xi, yi, xi plus 1. Okay, and then you choose an implicit method. We assume, we pretend to believe that one is y plus 1. We just keep using such a method. You don't need to solve it because the k plus 1 iteration. This ith iteration, right? Kth iteration. Okay, you just try this step, repeat this step as many times as needed. Yes, and actually it's until this estimated relative error is small enough. Now you say, oh, the solution is acceptable, therefore you get this value. You stop. Okay, the predictor corrector method. The predictor corrector methods, they're all stable. Okay, I believe it's so. Okay, so they tend to be very good. Okay, now we studied which theme? We studied Euler's explicit method, implicit method. Now, how about we combine the two? It's like this. We use the explicit method to initialize y plus 1, and now call the implicit method. Pretend that this guy is y plus 1, and you calculate a new value, you get a new value, keep updating y plus 1, you get a this, you may say this will refine this y plus 1, make it better and better. Okay, until that y plus 1 is acceptable, and then stop. So the LUO code is like this. Okay, you say, hey, first we set up a y1, that's which y? Y sub 1, that's y1, that's that's the initial condition, initial point. Okay, then you try to find a y2, y3. Okay, how to find a y2? First we use the Euler's explicit method to find a y2, and now we try to use the implicit method, okay, to get a new y value. And now you check this new value, and then the old y plus 1 is there. The estimated relative error large. If it's large, you just continue. You say, hey, that y plus 1 is new. I get a new value. Use which one? Euler's explicit method again, and just continue. And okay, just continue. Many times as until this guy is true, and then stop. Okay, so, and with the modified Euler's method, we can also, that's the modified Euler's method, and we can we change it to which one? To a predictor corrector method? Yes, you can do this way. Use the very one, that's Euler's explicit method to find y plus 1. And now use this, just do this again and again. Okay, and you find y plus 1, yes, until that 1 is acceptable. So it's quite, today's topic covers so many things. You need time to digest anyway. Hopefully this can help you understand, master all of those methods, and modified Euler's method, implicit explicit method, midpoint method, and the Runge-Kutta methods, and finally this predictor corrector methods. And we don't cover multi-step methods and solving. Now we just solved which one first order initial value problems. Have high order ones. You have sections in this very module to cover them. So okay, I wish you all love such a topic. Good, thank you.